So, show of hands. First of all, can you all hear me? Good. Okay, second question. Who here is a fan of trains and railways? Yep. And who here is a fan of computers? Yep, same number, roughly same number. And so how many of you have thought about if there's a connection between these two things? Well, if you have done, some hands here, great, then you are in the right place. So this is my talk, Riddles on Rails. My name is Dan Hagon, and it's going to be a fairly fast-paced talk. So we're going to start off talking a little bit about safety, so safety for computers, safety for railways. And then it's going to get a little bit weird for a little while, but stick with it, because at the end we're going to go and look at some fun puzzles and games. So just a little bit about me. So I design a wireless control system. It's a battery-powered system for model railways. And I've been coming to hacker camps now since 2011 or so. And it was kind of a surprise to me when I sort of looked at the history of sort of hacking and hacker culture, that the original hackers, the people that actually called themselves hackers originally, were actually model railway enthusiasts. So that you can sort of read about it in Stephen Levy's book here. It's called the Tech Model Railway Club. Still exists at MIT, but they were really into using computers to control their model railways, basically. So let's talk first of all about how we do safety, but not just safety for railways, but also for computers. And actually, there's a very strong relationship between the two. So I want to take you back now to 1861, and imagine it's sort of a bank holiday weekend. People have been to go and visit the pavilion. It's a very nice place in Brighton to visit. So lots of people are going to get on their trains and go home, to London or wherever. And so just outside of Brighton, there is a tunnel. It's called the Clayton Tunnel. It's quite an ornate tunnel, as most Victorian sort of buildings are. And on this particular morning, there were 3 trains that were due to leave, and as it is on one of these sort of busy mornings, they all were sort of very late to leave, and so they left at within a very short succession. And at the time, they were using sort of time intervals to. And you can see, the timings that, of the departures. Now they're using time intervals to leave to make sure when a train's gone. Don't send the next one until you've got enough time between it, okay? So let's have a look at the tunnel itself. So at the tunnel you have, the tunnel itself actually, you can't quite see all the way through the tunnel, so it has a slight kink at the end of it. So they have to have a signaller at each end of the tunnel, okay? And so they basically ensure entry and exit of the tunnel. And now at the entrance of the south side, as you can see here, there was a ball, basically, and it rose up to indicate that a train could proceed, and then it was dropped to indicate that, once a train had gone past it, it was dropped automatically. Okay, so let's just reset that and see what happened on this particular incident. So our first train goes past, okay, and then the signaller on the south side signals to the north side and says the train is now in the tunnel. Okay, nothing wrong with that. But then he notices something about the ball, so that ball hasn't dropped. Okay, so that's our first sort of failure that's happened. Okay, mechanical failure. Okay, so what he does then, he rushes out with his flag. Okay, and he's not quite quick enough because the next train's coming very shortly after. So he's not quite quick enough. He's not quite sure if that second train has seen that flag, okay? But he's quick enough to actually stop the third train that comes along. And then he can, he has a choice now. Does he send this third train into the tunnel, or does he wait? So what he does then, he sends a message to the other signal and says, is the tunnel clear? Okay? Now, just at that moment, the first train that went into the tunnel exits the tunnel. Okay? Now, that north side signaller now tells the other signaller via a bell, telegraph system. He says, yeah, the tunnel's clear. However, I think you can probably guess what's going to happen here. That second train is still in the tunnel, and that second train knows that flag was there, and he actually decides to reverse. Okay, that is also a failure that he should have he should have thought about the consequences of that. So what happens is fairly obvious, that the two trains collide, one reversing into the other. And actually, it's one of the most sort of kind of disastrous rail accidents, actually, sort of in rail history, in UK rail history. 23 people actually died in that particular incident. Now, the thing about it is, there are lots and lots of different ways you could actually correct this, and you can think about where the failure happened with this. Okay, so I'll leave that with you to kind of think about where you would correct the protocol that was going on there. Okay, so let's just have a look at a more modern way of doing signaling. So, if it's going to... Oh yeah, so there's a little link here for if you're interested in more of this. There's lots and lots of data on this particular site that tells you about other accidents and why they occurred and various things like that. Anyway, so let's think about in a station. So a signaller, the signal box in the station can see the whole of the station, and he can basically, he or she can basically look at all the trains that are there and determine whether or not they're going to collide and switch the points appropriately. But when you get to a tunnel, the situation is different. You basically, as we've seen, you can't actually see through the tunnel. And so you have to have a principle that you use to ensure that trains don't collide. Okay, so let's say we've got two stations, A and B, and we use what's known as the absolute block system. So we absolutely make sure that there is only ever one train in that block section. Okay. Okay, so how do we do this? Well, the signaller at station B basically has control over the line that precedes it, and the signaller at station A has to request permission for trains to come into that section. Okay, and how do they do that? Well, as we've seen, there's a telegraph system between them, so there's what they call a block instrument, as you can see here, and various sort of protocols for various bells that they use to say whether or not to request to come into a section and whether something has cleared the section and so on. Okay, so then what does the train driver, the engine driver, see? So at the entrance to the section, you've got a signal, and it's actually called a starter for fairly obvious reasons. And then you also have another signal at the exit to the block called the home, so when you get home, basically. And we can see actually what they look like. Now, notice something about the way that they are designed. So basically, the arm is raised for the proceed aspect, but if it fails, for instance, then it will fail in the fail-safe mode. Okay, so that's what's called upper quadrant. And the signaller knows that the train has left the section because you can see here at the end of the train there is a red light. That's really important. If the train breaks halfway through, then if he doesn't see that red light, then he knows not to allow another train into that section. Okay, so we've gone and seen how the railway operates and ensures safe operation from collision. How can we apply this to software? So here are two processes. They're basically running infinite loops, and they have two different sections. So they have a critical section, and they have a non-critical section, and then protecting the entry and exit from that critical section are two primitives called signal and wait. Okay, so very, very similar to the sort of block section that we've seen with the railway. Okay, now this was actually designed by a Dutch computer scientist called Edgar Dijkstra, and he actually used the names he originally used weren't signal and wait, but P and V, and they, I'm told, stand for equivalent concepts directly taken from the railway analogy, essentially. And so a semaphore, in this case, similar to the signal, allows entry and exit to the critical section, but it is just an integer. So basically, at the point the integer becomes 0, another process can take or gain entry to that critical section. And this basically, the critical section means that only one process is executing that, which means if you've got a shared memory region, that only one process can read or write to it. So that ensures consistency. So you can imagine if somebody's just read from a memory area, and they try to read from it immediately. Something else tries to read from it immediately. What will happen is that they will have inconsistent views of that data. Okay, so that's semaphores. Now let's look at another kind of safety issue. What we were discussing there was kind of safety from a sort of a policy level, but this is more about sort of what does the kind of human operator do in the system. Okay, so the trolley problem basically. So imagine there's a trolley that's barreling down the tracks and it's out of control. Okay, and then there's some people on the tracks. Now it's not quite explained why they're on the tracks, but bear with it for now. Okay, so you then have control of a point. Okay, so it's a fairly easy decision to make. You pull that point, except of course so there's always a catch. There's somebody else on the other track. Now there's only one person on the other track. So the kind of the decision process here is, well, what do you do? Do you sort of say, well, if I wasn't here and that train was just coming down that track anyway, well, you know, those 5 people would be killed, right? So if I wasn't here, that would happen anyway. So if I just leave the handle, it's the same thing, or is it? Okay. And then the other thing is, well, if I pull that handle, I've definitely, I mean, I've made that conscious decision. That one person is going to be killed, and that was my action that's done that. Okay. So I mean, there's no right answer to this, but it's one of these problems which, as in sort of in moral philosophy, moral ethics and philosophy and the rest of it, it has kind of created a lot of interest and debate, basically. So I was kind of curious, actually, this idea of people, people on tracks and it being a sort of trope that you get. I mean, you think of silent movies, but actually it kind of goes back a lot further. It actually goes back to a play by a guy called Augustin Daly, sort of a Victorian melodrama. And the trolley problem itself is sort of a 60s problem, although you'll see it crop up in sort of internet memes. There's lots of like quantum mechanics-based ones anyway. And so basically there's lots of sort of variations on this idea. Where does it get application? Well, autonomous vehicles. You think about AI in autonomous vehicles, right? So at some stage, that vehicle has got to make a decision. Do I swerve, to not hit a group of pedestrians? But what then happens to the passengers in my car? Okay, so this does kind of have applications. Of course, you could of course put the vehicle on some rails and make it a bit safer that way. But anyway, we'll use AI. That's the way to do it. Okay, so all right. So now it's going to get a little bit weird. So we're going to talk about time. So time. Well. So look at this clock here. What can you notice about it? It has 2 minute arms. Okay, so this clock is off the side of the Corn Exchange in Bristol. Okay, and these 2 minute arms are there because one is for London time and one is for Bristol's time. Now, this is at a time where all over the country everyone was setting their clock by the sun, basically. So there was completely inconsistent timing amongst all the different locations. So it was complete chaos, basically. And you have things like people would make their watch, run a bit faster when they were going from east to west or slower. Forgot the right way around. One of those ways around, anyway. So they correct for these timings, and you can imagine all sorts of things like accidents and people just missing trains. So they had to figure out a way of getting around this. So what they came up with was a time distribution system known as the chronopher. So basically, this ran along the telegraph wires. So you're using the pre-existing telegraph wires for signalling and so forth, and it basically. It basically became known as railway time as a result of this, actually, but it was used for more than just railway timings. Okay, so this is a sort of schematic of the timing. So of the chronopher system itself. So you can see on the top, what is it on your side? On the top left-hand side, you can see the incoming signal coming from Greenwich. Okay, this is the Greenwich mean time. And then there are 5, I believe, signals going out to various locations, and you can see the relays and the batteries at the bottom. Okay, so this time signal was sent at 10 a.m. every day. So they had to clear the telegraph wires were used for normal traffic, but they had to clear that line at 10 a.m. every day to make sure that they got this time signature coming through. And I'm reliably informed, even up to the 60s, this was still being used. used. And so, yeah, basically they'd listen out for this time signature, and then they'd relay this time signature out to many, many other locations, okay? So distributing it out. Now, we actually have a very similar situation actually in computing. So we've got something known as the network time protocol, and you can see the sort of the tree-like structure. So you can see it being distributed from a sort of essentially a sort of central source, so that you have multiple what they call stratum 0 clocks and various strata 1, 2, and 3, and so on. So in the UK, for instance, we've got the National Physical Laboratory. On camp here, we actually have a couple of time servers as well. So basically, you can see very similar kind of principles being used here. How do we actually use this to synchronize our clocks? Well, basically, timestamp messages will be sent and received between two different servers, and you'll use that to determine various things like offset and drift and so forth. And then something known as Mazzullo's algorithm, or slight variation on that, is used to combine time signatures from multiple clocks. So basically to get rid of outliers, as it were. Okay, so that was sort of the 19th century view of time, which we kind of still use today, actually. But back in the early 20th century, a chap called Einstein came along, and he thought a lot about time. Time was kind of important to him. So he has various thought experiments, and one of them involves a train. Now, he envisaged somebody on a train with a stone or a pebble or whatever, and they throw that pebble, and it hits the embankment, okay? Now, to the person on the train, the pebble is basically, I mean, they don't throw it, they let go of it. So through gravity, the pebble is just going vertically down from their perspective, okay? So to the person on the embankment, though, they're seeing as a parabola, okay? So he asked the question, basically, which is the one true path this pebble is, or the stone is taking. And so he thinks this through, and basically his conclusion is there isn't actually a one true path. So there is a path for each of these, what's known as these reference frames. So every reference frame basically has, so I'll move on to the next, there we go. So basically every reference frame, the laws of physics within each reference frame are the same. So there's no sort of special reference frame. So a lot of people look at this problem and they think, well, obviously the bank is bolted to the earth. It's the one true reference frame, and everything else is relative to that. But his conclusion is no, that all these different reference frames are equally their own particular reference frame. And one particular part of this is that the speed of light in each reference frame is the same. Okay, so we'll need that in just a second. Okay, so how does he use this then to think about time? Well, he imagines lightning striking either end of the train. Okay, he actually says hitting the rails, but it's the same thing, hitting the train effectively. Okay, so he's asking the question, are these events simultaneous? Okay, do these events occur at exactly the same time? Okay, and in particular, do they occur at the same time for the person stood on the bank, the embankment, as for the person stood on the train? Okay, so basically, let's think about the person on the embankment. So that person, let's imagine them midway between the two locations, okay? So we know that the speed of light is the same in that reference frame as any other reference frame. So she's in the middle of the two lightning strikes, and the light clearly is going to take the same amount of time to reach her, basically, because it's got the same distance to travel. So for her, if she sees those as simultaneous, if they really are simultaneous in her reference frame, then she's basically going to, they're going to arrive at the same time because they've had to traverse the same distance. And so basically, we can use this principle for a given reference frame to say, well, all these clocks within that reference frame are all synchronized. Okay, we can look at the position of the hands and we can say all these hands are pointing to the same position. Okay. Now let's think about the other reference frame, the frame that's within the train that's going along. Okay, so basically, if you consider the midpoint along the train, so that basically when the lightning strikes occur, that is the same as the midpoint for the embankment frame, but crucially, it's moving along. It's moving relative to the embankment. So actually, the light that's coming along the train from behind and the light that's coming from in front will take different amounts of time to reach that person, because by the time that person has got further along the track, the time that the light has reached them, they've got further on the track, and there's less time it takes for that light to get to them from in front of them than it does behind them. Okay, so there's a really, really profound conclusion for this, right? Which is that actually, to say that events are simultaneous, you cannot say that unless you say they are simultaneous in this frame of reference. Okay, that's a really, really crucial conclusion from what's known as special relativity. Okay, so you might think, well, okay, this is very esoteric. It doesn't really apply to everyday kind of things, speed of light and the rest of it. Well, actually, GPS, if you didn't correct for special and general relativity, within a day, you basically your position would drift so far that it would be next to useless. Okay, and so that's an everyday kind of usage of of these principles. But even on a network, we've got sort of differential time through the network, for delays in buffers and different line speeds and so forth. So within a distributed system, different times, different events occur at sort of different times, and you can't really sort of have a consistent view of timing. And also, you could have someone that purposefully says, well, this thing occurred at that time, or somebody along the way can maliciously change timestamps and so forth. So when you start thinking about it, time in distributed systems on the network is actually a really, really slippery kind of concept to kind of deal with. Anyway, so people have looked at this, and one of the concepts they've come up with is what's known as sort of logical clocks, or Lamport timestamps, or Lamport clocks. So basically, we've got three processes here, and we'll look at the middle one here. We've got various events that occur within a process, okay, and it's fairly easy to work out that they'll occur in time order. There's no problem there. Now, when we send a message between two different processes, well, I think we'll all agree that a message is sent before it's received, so then we've got some time ordering there. Okay, so what we have then is what's known as a partial order. So there are some events, for instance, these two here, which we can't actually say, well, that one occurred before that one, or at the same time as that one, and so forth. Okay, so it's a slightly weaker kind of notion of ordering events in the system. And so variations on this theme are what's in use at the moment for timing within distributed systems. So, okay, so that was the kind of weird stuff that's out of the way. Now I'm gonna skip one slide there, and I'm gonna talk here about. I will come back to that other slide, by the way. I'm going to talk about shunting yards, okay? And basically, there's a kind of puzzle that's known as a shunting yard puzzle. There's lots and lots of these, and this is one example. It's kind of the most famous example. So in this one, you have basically you got a shunter, and then you have 8 wagons, coaches. They're given numbers, and you have to. Basically, you've got different capacities on the two sidings. The 3 sidings, and on the spur. So the top 2 have 3, the bottom one has 5, and the spur has 4, but one of those is for the shunter. And so basically, you've got to shunt them, just using the rails that you've got there, basically. You've got to shunt the wagons so you get the wagons in the correct order, 1 to 5. Okay, so it's a fun kind of puzzle, and there's lots of variations on this theme. But you might notice a kind of similarity here with a puzzle that's kind of very often used in early programming kind of teaching and things like that. It's not quite the same puzzle, but it's a very similar puzzle. and as I say, there's all sorts of other variations on this theme. So we can also think about shunting yards in terms of basically grammars. So to generate a language, you need a grammar to say how you compose the various elements that are, the little the parts that make up words in that language. Okay, so normally you'd use something like Backus Nahr form, but this type of diagram is actually fairly. It used to be more commonly used, but not so much these days. For instance, Pascal used to use it as a way of defining their language. But this is exactly the context-free languages that you get with BNF form. So how do we use it? So let me give you an example. Oh, by the way, this one comes from the JSON specification, so I'm sure a lot of you are kind of fairly familiar with this now and again. So one example of this, so these are defining floating point numbers. So I've got one here which I can't quite remember. Well, anyway, that number there, whichever one it is, I think minus 0.24, has the following. You trace it through this path basically to get to define that number in that grammar. So let me give you a slightly more complicated example that takes a different path through that. Okay, so that's how we define that particular number. So let's think about now. So I want to go in two different directions. So I can define the sort of strings in my grammar, in my language using the grammar. But maybe I want to take a string and I want to decompose it and actually evaluate it. Okay. So first of all, let's define a grammar that we can use to do that. That operation. So we're going to do something based on single-digit arithmetic expressions. You'll notice this one does something that most shunting yards can't do, which is it's recursive. So you can take this entire diagram and place it in each of the two expressions, either side of the operator in the middle. Okay, so let's give you an example from this. Okay, so this example, I notice I've put the numbers in order. That will be important a little bit later on. So this example, we can't directly evaluate this, or the computer can't directly evaluate it. At least it's not easy for it to do so. But there is a form known as reverse Polish notation. You might also know this as postfix notation. The one at the top is actually infix notation, and this is actually an easier form to evaluate, because you can basically take the numbers and the operators in the order that they come. So, for instance, we'll have a stack, and we'll push our first value on the stack, and then we'll take our next value, push that onto the stack, and then we'll take our operator, and then we'll combine the two top values on the stack to create the new value, and then push that back onto the stack. And so then we can do this and many times over, and then we've evaluated the whole expression, and in this case it's 2. Okay, so we've got a problem here that we've got an expression in infix notation, and we want to need to get it into postfix notation. Okay, so in order to do that, we use something. So we need a way of doing that. Okay, and notice one thing. First of all, the numbers, when we convert between them, are in the same order, okay? But sometimes the operators are in different order. So we're going to do some we're going to do some shunting to get them into the right order. Okay, so how do we do that? Well, again, this comes from Dijkstra, and basically his mechanism of doing this basically uses a shunting yard. So let me quickly go through this. So we shunt our operators across to the siding, and then by doing so we can get it into the right format. Okay, and then just a final thing about Dijkstra. He is very famous for this thing called the Dijkstra's algorithm. It turns out that here in the UK, people working on the UK rail network back in the 50s came up with the algorithm just 2 or 3 years prior to him, and that is a very fascinating kind of story, and I urge you to kind of have a look more into that. But certainly a lot of these things crop up now again and again. Now I think I've run out of time. There were a couple of videos here, but I shall. No, I think Yeah, are we? Yeah. First one. Yeah, we'll do this one here. Okay. And that. Hold on. Oops. See if I can get this. Right. Thank you. So this is just a little puzzle here. So you might notice that the tracks in this particular orientation, they look like they're different lengths, but I can show you that they're exactly the same length, right? So go and get some track and try and figure out why that's the case. But I think that's the end. Okay, thank you very much.